Section 5.3 is definite integrals and antiderivatives. So first we're going to just go through the rules for definite integrals. You've seen these before. If I'm integrating from a to a, in other words, if the interval is 0 distance, my integral is always 0. The integral from a to b plus the integral from b to c is the integral from a to c, adding our integrals together. The order of the interval, or the order of integration, from b to a versus from a to b, they are opposites of each other. If I have a function times a constant, the integral of the constant times the function is the constant times the integral of the function, and this is for any number k. Here's another example from a to b and negative a to b, just a specific example when k is -1. So if we're integrating the opposite of a function, it makes the integral the opposite. If we're integrating, where am I, back here, if we're integrating the opposite direction of the interval, we also get an opposite integral value. Sum and difference. The integral of the sum or difference of two functions is the integral of the first function plus or minus the integral of the second function, depending upon which we are using, plus or minus. Max-min inequality. This is one that you may not have honed in on last year quite as much, but if the maximum of f and the minimum of f are maximum and minimum values of f on any interval, in other words, you've got a local max, a local min on a particular interval, then the minimum value of f times the interval is always less than the integral, which is always less than the maximum value of f times the interval. So in other words, if I have a function from a to b, if I take the minimum value of f on that interval and multiply it, I get this area. That's always going to be less than the actual integral. If I take the maximum level and multiply it by the interval, I'm always going to get a larger value than the integral. We're going to use that when we talk about bounds. And domination, if f of x is always greater than g of x on the interval, then the integral is always greater than the integral of f of x is always greater than the integral of g of x. If f of x is always greater than 0 on the interval, then the function, the integral of the function, is always greater than 0. This is the same rule as the previous one, just setting g equal to 0. So that's it for our rules. Let's take a look at some of these. And I hope you're listening instead of just watching. So, sorry, this is off the screen again. I don't know why it keeps doing that. But the example using the rules for definite integrals. So this is just using the rules. So suppose we have these three integrals, and then we want to find the integral from 4 to 1 of f of x dx, if possible. So take just a second and see what you come up with. So hopefully you notice that 4 to 1 is just the opposite of the interval from 1 to 4. So it's going to be the opposite value, or positive 2 instead of -2. Okay, here's another one. Again, the similar choices. Now we want the integral from -1 to 4 of f of x, if it's possible. So take a second, see if you can do that. Okay, so in this case, from -1 to 4, and I wish they'd show the in-between step, it's the integral from -1 to 1 plus the integral from 1 to 4. So in this case, that would be 5 plus a -2, which is 3. Okay, one more. Same choices up top, but now we're looking for the integral from -2 to 2 of h of x dx. So find that. And unfortunately, this one is not possible. The information is not given. Just because the limits of integration are doubled does not mean that the integral is doubled. Okay, finding bounds. So we want to show that the integral from 0 to 1 of the square root of 1 plus cos x dx is less than 3/2. So we're going to use some of that information from our max-min rule. So we know, we know by looking at this function that cos of x, we know, has a limited domain. It must be from 0 to 1. So if I plug in my minimum value into here, the minimum value for the square root of 1 plus cos x, if I plug in 0 for the cos of x, would be 1. So I know this has to be greater than or equal to 1. And if I put in 1 for cosine of x, which is the biggest value I can have for this, I know this has to be less than or equal to the root 2. So I know that the value of this integrand has to be between 1 and root 2. So therefore, my minimum value, somewhere my minimum value of my function is 1, somewhere it's root 2. The distance is from 0 to 1, so 1 times 0 to 1, I should put 1 minus 0, has to be less than or equal to the integral, which has to be less than or equal to a rectangle formed up here, which is root 2 times 1 minus 0. So therefore the integral is also going to be between 1 and root 2, and since 3/2 is greater than or equal to root 2, we can say definitively that this integrand will always be less than 3/2. Okay? If you have questions on that, we'll talk about it during class. Okay, the average mean value. If f is integrable on a to b, its average or mean value is the average function value. Find the integral, divide by the interval. So that gives us an average value. So let's look at that. Find the average value of this function. So we look at the definition, plugging in our interval and our integrand. We're going to use NINT. I know that at this point, having done all of the AB material, you know how to do that. But for right now, we're going to use the calculator. We get this for our answer, and therefore the average value is negative 10/3. Which leads us to, the mean value theorem. That's what it says up there, the mean value theorem for definite integrals. So again, if f is continuous, then at some point c, there will be some f of c that equals this mean value, or the average value, sorry. So here we are again. We can find a value c such that c, or f of c, times a to b, so f of c times our interval will equal the integral from a to b of f of x. Sorry, I ran out of room. Okay, so again, that mean value theorem, that finding the value of c such that the integral under the rectangle is the same as the integral under the curve. Okay, so now we get to the derivative of an integral. The derivative of an integral, this is just inverse operations. So if I take the derivative of the integral, I get the function value at x, whatever x may be. Now let's look at that. Integrals are antiderivatives of f. So suppose that f is an antiderivative. So the integral, if I derivate that, would be this function. So therefore, before I derivate it, I get the antiderivative. And we all know this form of our plus c. If I set x equal to a, then I'm taking the integral from a to a of f of t dt, which is f of a, the top bound, plus our constant c. Knowing from our zero property, if I integrate from a number to itself, that that's always 0, I can set this equation equal to 0, and I find that c is the opposite of f of a, which then brings us down from here to here, which I hope you recognize as the fundamental theorem. So let's look at that and see what we can do with it. So we're going to do the integral from 0 to pi, and we are looking to use the model we had a minute ago, the integral from a to x of f of t dt equals antiderivative of x minus the antiderivative of a. So in this case, we're going to find our antiderivative. The antiderivative of sine x is negative cos x, and we'll take, I got to plug in my x, sorry. So negative cos of pi minus negative cos of 0, using my two limits of integration. The cos of pi is negative 1, so negative of negative 1 minus negative of the cos of 0, which is 1. That gives me 2 plus 2, whoops, 1 plus 1, I'm a step ahead of myself, which is 2. So you've done this a ton of times, no problems. Just make sure you remember your rules about addition, the zero property, the ones we did at the beginning, and that you also take a close look at how we arrive at this magical equation. Okay, so I'm going to just scroll through these for you again. This is a quick quiz that's provided by the publisher. If you want to look through these just to kind of refresh your memory on our first 3 sections, great. If you don't, it's up to you. I'm going to scroll through, and the last couple screens are going to be the answers. So we've got just a couple questions. There's the first one. Oops, I'm sorry, it highlights the answer right after. My bad. There's the second one. Here comes the answer. There's the third one. Here comes the answer. And that's it. So just a quick quiz. Rewind, use it if you want. But that's it for this lesson.